All right, welcome to this explainer. Today, we're going to dive into something that honestly gets treated a bit too much like magic: machine learning. If you've ever wanted to peek under the hood and figure out how these systems actually work, well, you are absolutely in the right place. I want you to think of machine learning not as some mystical, unknowable AI wizardry, but simply as a highly structured toolbox. And inside this toolbox, just specific mathematical tools, algorithms, with each one designed to solve a very specific type of data problem.
So here is our game plan for today. We're going to start by opening up the machine learning toolbox, then move into predicting and classifying data. After that, we'll explore ensemble models and the power of teaming up, uncover some hidden data patterns, and finally, wrap things up with a handy cheat sheet for choosing the right algorithm.
Okay, let's jump straight into Section 1, the machine learning toolbox, setting the groundwork.
Before we start pulling out the really complex tools, we need to understand the basic materials they work on. Every tool in our supervised learning drawer relies on a very simple mapping. Your independent input variables are used to predict your dependent output variable. It doesn't matter if you're trying to predict tomorrow's stock price or just categorize a random email as spam, you are essentially asking the algorithm to mathematically map those independent inputs directly to a dependent output. It really is all about connecting the inputs to the outputs.
Moving right along to Section 2, predicting and classifying data. Let's look at the foundational algorithms.
Let's say you have a model and it predicts that the probability of your baby crying tonight is 0.05, so 5%. If you take that 5% probability and multiply it by the 365 nights in a year, you get 18. That means you are going to be waking up exactly 18 days a year to soothe your baby. This is actually a perfect illustration of logistic regression. It estimates the probability of an event occurring, and it ensures its output is always mathematically bounded between 0 and 1. That gives us incredibly concrete, actionable probability scores. Now, here's a funny quirk in data science. Despite the name, logistic regression is actually a misnomer. We don't use it for regression problems at all. Linear regression is what you use to predict continuous values, like house prices, by fitting a literal linear equation to your data. But logistic regression, it uses something called a sigmoid function to guarantee that value stays strictly between 0 and 1, and that makes it absolutely perfect for binary classification. Think spam or not spam, or determining if a tumor is malignant or benign.
You know the old saying, right? Birds of a feather flock together? Well, that is the exact philosophy behind our next tool, the K-nearest neighbors, or KNN algorithm. It's built entirely on proximity. KNN calculates physical distance, typically using Euclidean or Manhattan distance formulas, to find the most similar data points to whatever you're querying. The whole thing inherently assumes that similar points just exist near one another. You simply set K to the number of neighbors you want to check, and then the algorithm basically takes a majority vote to classify your new data point.
Next up in the toolbox, we have support vector machines, or SVMs. The goal of an SVM is to find a decision boundary, which we call a hyperplane, that distinctly classifies different data points. But what happens if your data is just a massive, jumbled mess and can't be cleanly separated by a simple straight line? Well, this is where something called the kernel trick comes in. It acts almost like a mathematical magic wand, transforming that low-dimensional data into a higher-dimensional space. Suddenly, in this new space, the data can be cleanly separated by a flat linear plane. And the best part? The algorithm doesn't even have to do the heavy computational lifting of transforming every single data point one by one.
Our last foundational classification tool is the naive Bayes classifier. This one is based on Bayes' theorem for conditional probability, and it works by maximizing probabilities to classify your data. Under the hood, it's really just doing simplistic multiplication, which makes it incredibly fast and efficient even if you don't have a ton of training data. But there is a catch, and it's exactly why we call it naive. It makes the massive assumption that all your features are fully 100% independent of each other. In reality, features are rarely completely independent, so that is a pretty big limitation you need to keep in mind.
Let's move on to Section 3, Ensemble Models Power in Numbers. This is all about teaming up weak learners.
When we want to combine multiple weaker models to make one strong one, we generally use two primary methods: bagging and boosting. Both of these start with a sampling technique called bootstrapping, where we create subsets of data with replacement. But how they use that data diverges wildly. Bagging, which is short for bootstrap aggregation, builds multiple independent models completely in parallel. It gives every model an equal vote, and the goal is to reduce the overall variance. Boosting, on the other hand, builds models sequentially.
Each new model specifically looks at the errors of the previous one, and it assigns higher weights to the misclassified data. It's aggressively trying to reduce the model's bias.
Let's ground this by applying it to actual algorithms. Take basic decision trees. They are incredibly intuitive, flowchart-like structures. But they are famously prone to overfitting and structural instability. So how do we fix that? Random forests! A random forest is a prime example of bagging. It builds a whole ensemble of varied decision trees in parallel, encouraging diversity by intentionally changing the root node for the different trees. Then it makes all these varied trees vote on the final prediction. That teamwork vastly reduces the overfitting you'd get if you just relied on one single tree.
Now, if random forests represent bagging, gradient boosting is our absolute powerhouse for boosting. Think of this process like a recipe, where every new step tries to fix the exact mistakes of the previous one. We start step 1 by initializing with a weak learner. Then we compute the negative gradients of the loss function. I know that sounds complicated, but it's really just a fancy way of saying we locate our residual errors. We fit a brand new model strictly to those errors, update our overall prediction, and then we just repeat the loop. We keep looping until a stopping criterion is met, and finally, we combine all those predictions into one highly accurate final model.
Okay, but you're probably thinking, a sequential process like that sounds incredibly slow for large datasets, right? Well, yes, it was. And that brings us to the power of XGBoost. Back in 2014, XGBoost just absolutely skyrocketed in popularity because it brilliantly solved this exact speed problem. It literally figured out how to parallelize an inherently sequential process. It does this by cleverly pre-sorting columns so it doesn't have to resort them at every single search. It uses a compressed column format, and it parallelizes the actual tree building across multiple threads or even multiple machines. This allows it to scale massively and crunch huge data sets with incredible efficiency. It was a real game changer.
All right, Section 4, Finding Hidden Data Patterns. Let's talk about unsupervised and temporal learning. When you don't have labeled data, how do you find patterns? Let's look at k-means clustering. K-means is a centroid-based method that finds underlying structures by minimizing the distance, again, usually the Euclidean distance, between totally unlabeled data points. Here is the core loop. First, you define k initial centroids. Then you assign every single data point to the nearest one. Next, you mathematically recalculate the center mean of those new clusters. And then you just repeat that process until the clusters stop changing. It's super powerful. But just note, it does work best when your hidden clusters are roughly spherical, and it can be a bit sensitive to exactly where you place those very first initial centroids.
But what if your data isn't visual clusters? What if we need to find hidden thematic structures in text? Enter LDA, or Latent Dirichlet Allocation. Think of LDA like a hyper-organized librarian sorting through a massive corpus of text documents to uncover underlying topics. And for time-based data, we use Hidden Markov Models, or HMMs. HMMs are brilliant for temporal sequence prediction, things like speech recognition or natural language processing. They operate on a really fascinating assumption that future states depend only on the current state. By utilizing hidden sequences alongside observable sequences, HMMs can effectively infer what's happening behind the scenes based entirely on what is visible to us. Now, at this point, you might be asking yourself, wait, where does deep learning fit into all of this? Ultimately, the biggest difference comes down to human intervention. All the tools we've discussed so far, like k-means and LDA, rely on explicit programming and feature engineering done by humans. Deep learning, however, automatically discovers those high-level features directly from the raw data during the learning process itself. Neither is inherently better. The choice between them depends entirely on your specific problem, the amount of data you actually have, and your available computational resources.
And finally, Section 5, Choosing the Right Algorithm. Let's pull out the ultimate cheat sheet. Here is your distilled comparative analysis of the toolbox. Need to predict continuous prices with low complexity? Pull out linear regression. Looking to detect spam emails or make a binary medical diagnosis? Logistic regression is your go-to. What if you're dealing with complex text classification or facial recognition? SVMs will handle that moderate to high complexity perfectly. Building a straightforward recommendation system? KNN is simple and intuitive. Or if you need to perform customer segmentation on completely unlabeled data, k-means clustering is the exact tool you want. Every single algorithm has its specific trade-offs across complexity, scalability, and ideal use cases.
So I leave you with this. Which mathematical tool will you reach for first to solve your next data problem? As we've seen today, machine learning isn't magic, not at all. It is a highly logical, meticulously structured toolbox.
Whether you are predicting an outcome, categorizing complex information, or uncovering hidden structures in massive unorganized datasets, success simply comes down to understanding your data and selecting the exact right algorithmic tool for the job. You now have the knowledge to open up that toolbox with confidence. Thank you so much for joining this explainer, and keep learning.